Okay, functions folks, we're back with lesson 1.7 part 2, which is going to be on the factor theorem. And there you see it, the factor theorem in all its glory. The remainder theorem leads us to a more important result. And the factor theorem is that x minus a is a factor of a polynomial f at x if and only if f at a equals 0. So if and only if the remainder is equal to 0, then we've got a factor. The proof of this, we went through the proof of the remainder theorem, but I'm going to put the proof of the factor theorem in a separate video. And if you're headed to university for math or for science or for engineering, and you know you're going to be taking math in first year, you should watch this. Again, you're not going to be responsible for reproducing the factor theorem proof, but it's good for you. It's good for your math soul, especially if you know you got more coming in the fall. Okay, so next fall in university. So this is going to be part 3. The proof of the factor theorem will be in a separate video. We're going to just go on and use it though. There's the beginning of the proof. So we're asked to factor it. Now we know that if I call this f at x, by the factor theorem, if I can substitute in x and make this thing equal to 0, then I know it's a factor, it being whatever I substituted in for x. So I need to try stuff. So try putting in 5 or 7 or 12 or -3 or 8 or 1 or 2. Now I've got an infinite number of answers. This doesn't seem like it's any easier. Well, that's where the warm-up comes in. What numbers should we try? Well, back to the warm-up, way back to the warm-up, back, right here, right? This is a factored version, and we know the n thing, the n number, the d, are all of the number parts multiplied together. So if I think about that carefully, once I get this in factored form, I'm going to have blah times blah times blah, and I know the first number is going to be x times x times x. These numbers here, whatever they are, they have to multiply to get to 24, right? Blah times blah times blah, that has to be 24. So it doesn't make sense for me to try 5 or 7 because those numbers don't divide into 24. So what are the numbers that we're going to try? Well, 1 divides into 24, 2, 3, 4, yeah, there's lots of possibilities, but we'll see as soon as we get one of them, we're off to the races. So we're going to try. We're going to try, say, start at the start, try f at 1. F at 1 is 1 cubed minus 5 times 1 squared, and you're going to get good at doing this in your calculator or in your head. 1 minus 5 minus 2 plus 24, which is not 0. So what can I say? Therefore, x minus 1 is not a factor. So then I got to try something else, right? I don't have a factor, so I'm going to try maybe f at 2. And I think this one might actually work. 2 cubed is 8. Minus 5 times 4 is 20. Minus 4 plus 24. No, that doesn't work unless I goof that up. It's getting close though, isn't it? So what does this say? This says x minus 2 is not a factor. And this is one of the advantages in class. We'd have 15 people punching away at their calculator. Somebody's going to hit one soon, and so I'm going to keep trying. Maybe we'll try f at 4. So I go 4 cubed minus 5 times 4 squared minus 2 times 4. I'm trying 4 because 4 divides into 24, and this one works. Pretty sure. Minus 8 plus 24, and that's equal to 0. So since we've found a value of x that makes this polynomial 0, we know the remainder is 0 when x minus 4 is divided into this. So therefore, x minus 4 is a factor. So what does that mean? That means one of these brackets is x minus 4. How do I find out the rest of them? Well, I could just keep guessing and checking, right? I could, but now I could just use long division and figure out what's left after I factor out x minus 4. So what do I need to multiply so that when I subtract, x cubed goes away? Well, x squared works. What's nice about the long division in the using the factor theorem is I know what the answer has to be. It has to work out perfectly. The remainder has to be 0. So let's see if that works out. That's 0 there. Negative 5 subtract negative 4 is negative 5 plus 4 is negative 1x squared minus 2x minus x is the next factor. There's the next number to write down. Subtract, bring down the 24, and I know it's got to be 0, so it's got to work out. So I write down minus 6 and negative 6 times negative 4 is positive 24, and it works out. And this has to be true, otherwise I goof something up. And now notice that this quotient is a grade 10 easy trinomial. So then I can say, therefore, f at x equals divisor times quotient plus the remainder is 0, but now this thing factors, grade 10 style. Numbers that multiply to get negative 6 and add to get negative 3. There are the factors. This is it factored entirely. All right, well, let's keep going. There's one expression factored. I think I got one more example, and then, yep, look at that. Homework time. The light is at the end of the tunnel. If I call this f at m, then I'm looking for values of m that will make this expression 0, and if I can find one, then I know I've got a factor. So, and this is actually a pretty tough question, by the way. F at 1 is 1 minus 6 plus 3 plus 2. That is 0. So therefore, x minus 1 is a factor. Right? And now, how do I get the rest of the factors? Well, I'm going to use long division. Oops. Not x, it's m. What am I doing? Doesn't matter. I guess you could have just changed those to x's. Notice that I'm going to have to put a placeholder in here because there's no m cubed term. And long division, m cubed minus m cubed, subtract, and I get m cubed. I'm going to have to move my homework out of the way here. Running out of room. Long division minus m squared. Get rid of this for now. Fine, you get it. Get out of there. Get. Subtract, watch your signs. But I do know one thing that's nice is that I know it's got to work out, right? Minus 5m plus 5m. Subtract, and I get minus 2. The 2 comes down. And yep, it's going to work. Awesome. But look what happens here. This thing that I'm left with is still a cubic. How do we factor it? Well, it doesn't factor grade 10 style. I'm going to have to go at this again. I'm going to have to use the factor theorem on this. Wow. Okay, no problem. Well, if I look carefully, if I just put in 1, it's not going to work. I can see that, but maybe -1 will work. Let's try, not f, this is g now at -1. And I get bing, 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 bing. I think this works out anyway. I hope. +1 +5 -2. Of course it doesn't work. It doesn't work. So what do I say? M +1 is not a factor. Well, we don't want to be here all day. Let's try g at 2 again. So g at 2. And that's 8 +4 -10 -2 is 0. So therefore, m -2 is a factor. What a question. I had to move the homework down twice here. Well, what do I do now? Now, notice that if I took my m -2 and divided it into the original polynomial, I'd have a different cubic. So I need to divide m -2 into this piece so I can figure out what's left after it goes into this smaller one. So, all right, here we go again. You're fast forwarding, aren't you? You don't want to see me do the long division anymore. Maybe you're using synthetic division. Maybe you figured that out. It's a little faster. Ask your classmates who have tried it. It's a little bit faster. I'm sticking to long division though. The old methods are the best. Okay. And I know this has got to work out, so when I subtract, I get m -2, that's +1. M -2, 0. So then therefore, finally after all that work, f at m is equal to that factor plus this factor, or times this factor, not plus, times this thing. Now, this thing is a grade 11 trinomial, but this thing here doesn't factor any further. What are numbers that multiply to get 1 and add to get 3? Well, it doesn't factor. Wow, long question. Long question. Could have we sped things up a little bit? A little bit, because what I could have done, and this solution isn't for the faint of heart, so if you're happy with this solution the way it appears, that's fine. You can stop the video now and go straight to the homework. But what I could have done is I could have used the factor theorem twice, found those two factors, and put them together, right? I could have put them together, and then I would have had m -1 times m -2 is m squared minus 3m plus 2. And then I know that this goes into f at m, right? This divides into f at m. So I could have divided that into my original expression. What was the rest? -6, 3, and 2. And then when I divide, what I'd be left with, when I divide the quadratic, I'd have m squared plus 3m plus 1. Now, how do I know that without actually doing it? Well, that's what the other factor had to have been, right? And so doing it this way, how is it faster? Well, I've saved myself one long division, haven't I? That's it. When do I have to worry about doing a second long division? Well, it's when I started with a quartic. When I start with a quartic, yeah, I take a factor out, use long division, I end up with a cubic, and then I have to go again. sometimes I can save the one step by putting two factors together. All right. Like I said, not for the faint of heart. There's your homework. Off you go.